Hello everybody, my name is Imane. Welcome back to my YouTube channel. Today we're going to go ahead and finish the second part of chapter 19, and we're going to continue our discussion about nucleophilic addition reactions that happen in ketones and aldehydes. We're going to pick off where we started. We covered oxygen and sulfur nucleophiles last time. So today we're going to start off with nitrogen nucleophiles and their reactions with ketones and aldehydes. There are two ways amines can react with ketones and aldehydes. Primary amines result in imine products, and secondary amines result in enamine products. And we're going to discuss both of those now. Now, in mildly acidic conditions, an aldehyde or ketone will react with a primary amine to form an imine. Imines are compounds that possess a carbon double bonded to a nitrogen, and these are really common biological pathways, and sometimes you'll see a little bit of this when you take biochemistry. Now, just like the oxygen and sulfur nucleophile mechanisms we discussed last time, we're going to break down this mechanism for imines into two major steps to help us remember it better. All right, so we're going to zoom in here. The first three steps, all right, this nucleophilic attack followed by two proton transfers, all right, is going to lead us to produce an intermediate called a carbonyl amine. And the last three steps of this mechanism is going to take that carbonyl amine and have a proton transfer, a loss of a leaving group, and then a final proton transfer to lead us to our final product, which is an imine. All right, now our imine product looks like this. All right, so this is the result of a ketone or aldehyde reacting with a primary amine. All right, this is an important thing to note. All right, imine formation is the consequence of a ketone or aldehyde reacting with a primary amine. All right, and just comparing the two, all right, reactant to product here, all right, we notice, right, this double bond is no longer to an oxygen anymore. It is to a nitrogen in our product, and this nitrogen is going to have some sort of R variable group, an alkyl group attached to it of some sorts. Okay, now in acidic conditions, an aldehyde or ketone can also react with a secondary amine, all right, to form an enamine. All right, enamines are compounds in which the nitrogen lone pair is going to be delocalized by the presence of an adjacent carbon-carbon double bond. Now, this mechanism for enamine formation is identical to the mechanism that was shown for imine formation, except for the last step and the fact that our ketone and aldehyde is initially reacting with a secondary amine. All right, for imine formation, it was primary. For enamine, it's a secondary amine. All right, then we go through the same essential steps of nucleophilic attack and two proton transfers to get to this intermediate of a carbonyl amine, where it's pretty similar, except here, all right, our nitrogen group is secondary, whereas here it was primary. All right, so those are the main differences to note between the two. All right, now the final three steps are, again, proton transfer, loss of a leaving group, and then a final proton transfer to result in this enamine product. Now, looking at this reactant, right, this is the starting material, if you will. All right, our starting material. All right, and looking at our product, okay, there is no longer a double bond here where it used to once be attached to the oxygen. It is now adjacent to, right here, if my pen will work. All right, and now we have a single bond here with a nitrogen that has a lone pair. All right, this is what we were talking about. All right, these enamines are compounds in which the nitrogen lone pair, all right, is delocalized by the presence of this double bond. All right, and remember, because we treated this ketone and aldehyde with a secondary amine, this nitrogen has these two R groups. All right, these two alkyl groups that are attached to the nitrogen. All right, here's another way to compare. All right, you can start off with, say, a ketone. All right, this works for ketones or aldehydes, remember, but we're starting here with a ketone. All right, we can treat it with a primary amine, or we can treat it with a secondary amine. All right, and it goes through some of the same steps here of nucleophilic attack and two proton transfers. All right, and then you form this this intermediate that we call the carbonyl amine, I'm sorry, all right, where the only difference here, again, this is a double bond to a nitrogen that has a positive charge. The only difference is this is primary, a primary carbonyl amine, and this is a secondary, all right, and this is our intermediate step. All right, and then we have the same last few steps of proton transfer, loss of a leaving group, and then proton transfer, all right, via either a primary amine again or a secondary amine, all right, and what we result with the use of a primary amine the whole time is our imine product, all right, where you have this carbon double bond to a nitrogen with that is primary, or if you use secondary amines throughout the mechanism, then you end up with an enamine product where you have a carbon single bond to a nitrogen that is secondary and your double bond is nearby, all right, adjacent, if you will. All right, so those are the differences between imine and enamine, all right? Imine is the consequence of a ketone or aldehyde reacting with primary amines, and enamine is the product of reacting a ketone or aldehyde with a secondary amine. All right, so keep that in mind. We're going to go ahead and jump into some practice problems to make sure we understand this. Okay? So here we have all right, we want to react this, all right, with a primary amine. Look at that. That's a primary amine. All right, so we know with this information, all right, we're starting with a ketone, all right, and our reagents, our main reagent is this primary amine. All right, we know that the end product is going to be our imine product. All right, so what that means is it's going to look like this. And we're going to go ahead and draw this like 7-membered ring or something. All right, very ugly, don't judge me. All right, this double bond to an oxygen is no longer a double bond to an oxygen. It's now a double bond to a nitrogen. All right, and its R group is just another hydrogen. All right, since it's primary, it's actually like not even primary. All right, so this is our final product here. All right, now what if we take B? All right, here's B. We have a ketone once again. All right, and we're reacting it again. This is a primary amine. Okay, so we know ketone, primary amine. What we're going to get is an imine product. All right, so what that's going to look like is we're going to draw. All right, it's no longer a double bond to an oxygen. It's now going to be a double bond to a nitrogen. All right, and then this nitrogen is a primary. All right, what's that other group that's attached to the nitrogen? It's going to be this ring structure right here. So this is what our product would look like. All right, now let's do C. All right, C is interesting, okay, because here's our aldehyde group. All right, and here's the nitrogen nucleophile that it's going to be reacting with. It's intramolecular. All right, so this molecule is going to react with itself. We have our primary amine right here, and it's going to react with this aldehyde. All right, so what that means, it's going to be a cyclic compound that we're going to form because one part of the molecule is reacting with the other, and it's going to form this closed ring system, a cyclic system. Now, how do we know how many carbons it is? Easy. Let's count. 1, 2, 3, 4, and nitrogen is going to end the ring. All right, so it's going to be a 5-membered ring where one of the points is going to be nitrogen. All right, so we're going to do 1, 2, 3. Let me do this better. 1, 2, 3. I cannot do this right. Like so, and the nitrogen will be at this corner here. I'll draw it better. All right, now again, all right, this double bond right here is no longer to an oxygen, it's to a nitrogen, all right? And that's within the ring structure that is formed to the nitrogen, all right? So again, we have our aldehyde reacting with a primary amine, and it's going to be attacking it right here to form a closed ring structure, all right, where we have still our 4 carbons, right? Here, let me erase this and do this better. Explain it a little bit better, right? This nitrogen is going to be attacking and forming a ring structure here where this is our first carbon, our second carbon, our third carbon, and this 4th carbon that's going to be double bonded to our nitrogen now, and it's going to form this 5-membered ring that we just drew here with the nitrogen double bond within the ring. All right, fantastic. Now I'll leave D to you, all right, but let's move on here and do a few of these right here. All right, so we have this starting material, all right, and it's reacting with a secondary amine. Okay, we have a ketone reacting with a secondary amine. That means our product is going to be an enamine product. All right, and we're going to go ahead and try to draw that. Let me erase our practice of imine products and let's get into enamine. All right, so for 1920, for A, all right, we have a ketone reacting with a secondary amine. We know our product is going to be an enamine product. All right, so what that means is, let's draw the ring structure here.
The time is 8:50 p.m. Have a good night.
Oh, you probably heard my Alexa in the background there. She's just talking to herself, I guess. All right, fantastic. Here's our ring structure. All right, this once double bond to an oxygen, all right, through the mechanism of trying to form our enamine product is actually going to turn into a single bond to a nitrogen, and instead our double bond is going to be adjacent to that. Okay, now this nitrogen is a secondary nitrogen, all right, and we're going to preserve that structure that's attached to the nitrogen here. All right, that doesn't disappear. So what that means is our nitrogen, yes, it's single bonded to that carbon now instead of double bonded, but the 2 groups that are attached to the nitrogen that make it secondary, all right, no changes are made to that. So this 1, 2, 3, 4 carbon that it's attached to, all right, is still preserved here. And so our final product looks something like this. We have this single bond to nitrogen where our carbonyl group once was, all right, that double bond moves 1 carbon over, all right, it's adjacent, if you will. All right, and we draw our nitrogen with the 2 groups that are attached to it that make it secondary, as we did for our imine products where we attached the group that made the nitrogen primary to the nitrogen after the process. All right, so let's go ahead, let's do one more, why not? All right, let's do B, and I'll leave C and D for you to figure out. All right, B, all right, here is our ketone. All right, and this is, guess what, a secondary amine. All right, so that means what our product is going to be an enamine product. All right, where our ketone, which looks like this, I can't draw to save my life today. All right, this ketone is no longer a ketone, but it becomes a single bond to a nitrogen, and we have our double bond adjacent to that. And then, of course, we want to preserve the 2 groups that are attached to the nitrogen, all right? And we're just going to try to draw that right, okay? And so this is what our product will look like. If you want to make this easier for you, instead of drawing the ring structures, we could just write our 2 phenyl groups. Fantastic. Now, as a quick note before we move on to hydrogen nucleophiles, all right? One more thing about nitrogen nucleophiles. Something interesting we can do, all right, is use, all right, a hydrazine, or a hydrazone, I'm sorry, all right, as a nucleophile with a ketone to form a hydrazone. Sorry, let me repeat that. We can use a hydrazine, okay, this is a hydrazine. We can use it as a nucleophile with a ketone to form this hydrazone, all right, where we have our double bond to nitrogen, all right, and then like another amine group attached to that nitrogen, all right? This is called a hydrazone, okay? We can take this hydrazone and go further. We can reduce it via a Wolf-Kishner reduction, all right? These hydrazones are actually easily and readily reduced under strong basic conditions, all right? And this process, this transformation is called Wolf-Kishner reduction, and it's pretty much like this two-step procedure for reducing a ketone to an alkane. All right, so you can essentially go from ketone to imine to an alkane. All right, again, this is going to be a really useful technique when we get to synthesis and synthesis strategies and techniques at the end of the chapter. So we can go from hydrazone using these set of reagents right here, all right, to completely reduce this group. All right, so what we have here now are just hydrogens. All right, this is the mechanism for this. All right, you start off with a proton transfer where one of the protons is removed and you form this resonance stabilized intermediate. All right, followed by another proton transfer and another proton transfer, and then you have nitrogen gas that is expelled, okay, and then one final proton transfer, okay, will give you your reduced final product. All right, so this is going to be really useful when we start to do synthesis problems, right? We have this starting material, we have this end product, we're trying to get from one to the other. We might potentially make use of the fact that we can take a hydrazone and form from a ketone to a hydrazone and then reduce it through Wolf-Kishner. All right, this might be a very good technique through doing some of our synthesis problems, so keep it in the back of your head. All right, with that being said, we're going to go ahead and move on to hydrogen nucleophiles. All right, when a ketone or aldehyde is treated with a hydride reducing agent like lithium aluminum hydride or sodium borohydride, aldehydes and ketones can be reduced to alcohols. All right, the mechanism of action for these reagents is a little bit complicated. All right, we're really just going to worry about the simplified version of the mechanism as opposed to the full blown out mechanism, again, because it's complicated. All right, so really it's just two main general steps that we're going to summarize it to. You have your ketone or aldehyde, you have your hydride reducing agent like lithium aluminum hydride. All right, you have a nucleophilic attack and then a final proton transfer, and boom, you've formed a alcohol. All right, now again, in the first step of the mechanism, your reducing agent is essentially delivering a hydride ion. It's going to attack the carbonyl group. You're going to form this alkoxide intermediate, and then this intermediate, you treat it with a proton source, and boom, you get your product. All right, again, this is a very simplified mechanism. This is not the full mechanism, but we really don't need to worry about the full mechanism here. Instead, we want to understand how to identify when we're treating a ketone or aldehyde with a hydride reducing reagent, and then how to draw the product of said reaction. So that is what we're going to practice here. All right, so we're going to look at our starting material. We have a ketone, and guess what? Our reagents here. That's a hydride reducing agent. This is good old lithium aluminum hydride. All right, what it's going to do is it's going to take this ketone, all right, and convert it to an alcohol group, okay? Like we said before, we keep this stays the same, all right, but now our double bond carbonyl is no longer a double bond carbonyl. It's an alcohol group. Now, notice something important. Excuse me. What we form here is a chiral center. So that means your product is actually racemic, all right? You get both enantiomers as products, okay? So that's an important thing to note here when you're doing these kinds of reactions, all right? Again, here we have an aldehyde. Hey, we have sodium borohydride. This is also a hydride reducing agent. So that means this, this carbonyl is going to be converted into an alcohol group, okay? So let's go ahead and draw that out. So instead of this double bond to an oxygen, we now form an alcohol group there. Of course, the hydrogen is still there. You don't have to draw it necessarily, but it's there. Fantastic. Let's do one more, and I'll leave the last one for you to try and solve. All right, again, we have our carbonyl group, and look at that. Lithium aluminum hydride. This is a hydride reducing agent. That just means that now our carbonyl is going to be a alcohol group. Once again, guys, this is a chiral center we formed here. So this is actually going to be racemic. We're going to get both enantiomers as products. All right, that's important. All right, might cost you a few points if you don't make note of that, if you have a free response problem like that. All right, so be careful. All right, now, last but not least, we're going to investigate reactions of ketones and aldehydes with carbon nucleophiles. All right, one very important reaction to learn is the Grignard reaction. And you're probably going to do a Grignard reaction in your organic chemistry lab. It's very important, very useful in synthesis. All right. So when treated with a Grignard reagent, all right, aldehydes are gonna be converted into alcohols accompanied by a formation of a new carbon-carbon bond. So what we have here, all right, whenever we have some alkyl group along with magnesium and bromide here, all right, and water, this is what we refer to when we say Grignard reagents, all right? It looks very specific. It's some sort of alkyl group, right? You can write it as R, MgBr, all right, and water. This is Grignard reagents. This is what we are referring to when we say that, all right? So when you take a ketone or aldehyde, all right, and you treat it with Grignard reagents, not only does this group turn into an alcohol, all right, but you attach whatever R group that you have, whether it's a methyl or an ethyl or a phenyl, all right, at the same carbon that you formed that alcohol. All right. So once more, when treating with a Grignard reagent, aldehydes and ketones are going to be converted into alcohols accompanied by a new carbon-carbon bond, all right, to whatever alkyl group you're going to attach there. That is part of your Grignard reagents. Your Grignard reagents is going to show you clearly what that alkyl group that you're going to attach to it will be. All right? Now, if you form a chiral center, all right, like you see in this example right here, okay, remember that you're going to get a racemic mixture of enantiomers, all right? That's very important that you make note of that, especially if you have a free response in a homework or test problem, all right? You can't just draw this and not make note that it's actually a racemic mixture of enantiomers that you're going to obtain as product. Also, these reactions are not reversible, all right? So once you treat a ketone or aldehyde with Grignard reagents, it's generally not reversible because carboanions, and we'll see this in the mechanism, all right, are not going to generally form as leaving groups. They do not function as leaving groups, so it'd be hard to go back, all right? And we could take a look at the Grignard mechanism. Again, this is a simplified mechanism of a Grignard reagent with a ketone or aldehyde. Essentially, you have your Grignard reagent, you have your ketone or aldehyde. Your Grignard reagent is going to function as a nucleophile and attack your carbonyl group, all right? And then the resulting alkoxide ion is then protonated to give you that alcohol group plus, all right, whatever R variable group, whatever alkyl group you're going to attach there. All right, we're going to get into a few problems in 1 second, but let's discuss also another carbon nucleophile addition reaction that can happen with ketones and aldehydes, and this is called cyanohydrin formation. All right, when you treat a ketone or aldehyde with hydrogen cyanide, right, or HCN in other words, all right, your ketones and aldehydes are converted into cyanohydrins. All right, and this is characterized by the presence of a cyano group, all right, and an alcohol group, a hydroxyl group, all right, connected, guess what, to the same carbon, all right? So this reaction usually requires mildly basic conditions, and the mechanism for this reaction involves a nucleophilic attack followed by a proton transfer, all right? So essentially in your first step, excuse me, my allergies are acting up. In the first step, a cyanide ion attacks the carbonyl group, and this results into an intermediate that is then your HCN obstructs a proton generating regenerating a cyanide ion. And in this way, your cyanide functions as a catalyst for the addition of HCN to the carbonyl group. I forgot to put the mechanism here, but it should be in the David Klein book. I'll put it in the notes, no worries. But anyways, the point is, when you treat an aldehyde or a ketone with hydrogen cyanide, all right, what you're going to do is form a cyanohydrin, all right? And that means that now you have a cyano group and a hydroxyl group connected to the same carbon, all right? These are really useful in synthesis because what you can do is you can take the cyano group and you can further treat it to yield some other kind of range of products. So in this first example you see here, right, this is a cyanohydrin that can be formed, all right, using HCN, and you treat that with a ketone and aldehyde, you can form this, but then you can take this and treat it with a hydride reducing reagent like lithium aluminum hydride, and what happens is this CN group gets converted into an amine group. All right, look at that. Just by treating this a cyano group with lithium aluminum hydride, you can convert it to NH2. That's fantastic. This can be a very useful technique, again, when we get to synthesis problems. Now, something else you could do, all right, you could treat it, the cyano group can be hydrolyzed to, guess what? Give us carboxylic acid using H3O plus and some heat. And then you can take that cyano group, you could convert it to a carboxylic acid. All right, this is really cool. We could do a couple things with these cyano groups, and this will be very useful, again, when we get to some of these synthesis questions. All right, now, let's do a few practice problems before we continue on with more carbon nucleophile problems, okay? So here, this question says, predict the major product for each of the following. All right, so here we have our good old ketone, and look what, this looks exactly like Grignard reagents. Okay, we know how Grignard reagents work now. What we get as a product is now our carbonyl is no longer a carbonyl. Instead, it's an alcohol group, and then whatever alkyl group we have attached to the magnesium bromide. In this case, we have ethyl. So we have an alcohol group and an ethyl attached to the same carbon. All right, so this is our product. All right, let's look at B. We have an aldehyde, and again, guess what? This looks like our Grignard reagent. We have some alkyl group attached to magnesium bromide and water. All right, we know what this is going to look like. All right, what this is going to look like is that this carbonyl is no longer a carbonyl. Instead, we have an alcohol group, all right, and then whatever R group we have attached to the magnesium bromide, and that's a phenyl. That means it's a phenyl. The pH stands for phenyl. So we're going to go ahead and try to draw that appropriately, like so. All right, fantastic. And that's what our product looks like. It's actually kind of ugly. Let me draw this better. All right, so this carbon that once used to be a carbonyl is now an alcohol and our phenyl group, because that was what's attached right here to the magnesium bromide. Fantastic. I'll let you do C now. All right, this is all Grignard reagents, so keep that in mind. But let's do some cyanohydrin formation problems. All right, so here, predict the major products. All right, we got our reagents in our first step that are gonna result in a cyanohydrin formation. All right, so just with the first steps, what that means is we're going to get a cyanohydrin product. And that means our carbonyl, no longer a carbonyl, it's an alcohol group, all right, and our cyano group, all right? But that's not it. This is not the final product, because look at our next set of reagents. These are hydride reducing reagents, all right? So what that means is, we just talked about this, whenever you have a cyano group, all right, and you use some reducing reagents, you're actually going to convert the CN group to a primary amine group. All right, so this is going to look like this. We still have our alcohol right here, beautiful, but this carbon This carbon is no longer triple bonded to a nitrogen. Instead, it's a primary amine. All right, so this is our final product. We did our cyanohydrin formation in our first step. Sorry, we did a cyanohydrin formation in our first step. All right, and then we converted that cyano group into a primary amine using reducing reagents. I'm going to let you attempt B. Let me know if you have any questions. All right, but with that, next up is a third carbon nucleophile reaction. This is called the Wittig reaction. All right, this reaction is going to convert a ketone or an aldehyde into an alkene by forming a new carbon-carbon double bond at the location where the carbonyl group once was. Now, the mechanism for this reaction is interesting. All right, there is strong evidence that the first step is actually a 2+2 cycloaddition process, and then the nucleophilic carbon of the Wittig reagent attacks the electrophilic carbon of the carbonyl group, and there is a concurrent formation of a oxygen phosphorus bond. All right, this is going to result in this four-membered ring here as an intermediate, but then this undergoes fragmentation to give our final alkene product. All right, so I mean, technically the mechanism for this is a little more complicated, but for now, this is good. All right, this summarizes what happens. 2+2 cycloaddition, you get this four-ring intermediate that then fragments. All right, easy peasy. Now, what happens? What happens if your Wittig reagent, which by the way is this phosphorus group, this oxaphosphatine group, what happens if your Wittig reagent contains a group? All right, what happens if it contains a group? What if instead of these two hydrogens right here, there is something else? What happens then? Well, if your Wittig reagent, all right, has just a simple alkyl group. So here's the carbon, all right, of your Wittig reagent. Let's zoom in here. Actually, let's look at this first one right here. Let's take a good look at this Wittig reagent. All right, let's take a second to stare at it. All right, what's happening? Yes, we can look at the mechanism, but in short, all right, in short, you're going to be replacing this oxygen right here with this carbon of the Wittig reagent. All right, so you're replacing that oxygen with this carbon. Whatever is attached to this carbon, all right, is gonna stay there. So these two hydrogens are gonna stay with the carbon when it goes through the cycloaddition and then fragmentation, right? And this is what you get here at the end, this alkene group that you're so interested in. All right, it's like switching this carbon and oxygen. That's why you get this as a subproduct as well. Now the problem here that we're trying to figure out is, what if it's not two hydrogens? What if, for example, your carbon has one hydrogen and then a methyl group? How do you know what your product looks like? All right, how do you know what your product looks like? Well, if you're dealing with just a simple alkyl group like this methyl, then your major product will be the cis or Z product. All right, so if you have just a simple alkyl group, remember, we're switching out this oxygen with this carbon right here. I'm going to highlight it in yellow. This oxygen is switching out with this carbon right here. Look at that. There it is. All right. We have to keep the hydrogen in the methyl group. But does the hydrogen get added here and the methyl group here? Or the other way around? Does the hydrogen get attached here and the methyl group here? Right? That's the ultimate question. Well, the answer to that question is, well, they get added to give us the cis product as our major product. All right, that means if you cut the double bond in half, the two biggest groups are on the same side. Look at that. The methyl group and the phenyl group are on the same side. Those are the two biggest groups. The hydrogens are on the other side. So this is the case when your Wittig reagent has a simple alkyl group. But if your Wittig reagent contains some electron withdrawing group or any other group that can stabilize the carboanion, right? For example, like some sort of carbonyl, all right? Then your major product is the trans product or the E product, all right? So let's look at this really quickly. All right, here's our aldehyde, good old aldehyde. Here's our Wittig reagent. Okay, here's the carbon. Let me do it in orange. All right, here's the carbon that we're going to switch out with the oxygen. That oxygen is no longer going to be an oxygen. It's going to turn into a carbon in our product. Now, the question comes, well, which side should we add the two groups that are attached to that carbon? Well, they go in the place where our major product here is going to be trans. All right, so if you divide this double bond, you want your two biggest groups to be on opposite sides of the double bond. Your trans is your major product when you have a group attached to your Wittig reagent that is an electron withdrawing group or anything that can stabilize your carboanion. Carbonyl being a great example of that. All right, so if it's a simple alkyl group, your major product is the cis product or the Z product, if you will. All right, if it's any other group like an electron withdrawing group, a carbonyl, something like that, your trans product is your major product. All right, so keep that in mind. Now, the general rule is the major product will be your trans product over your cis unless it's a simple alkyl group. All right, where E refers to trans and Z cis. In other words, whatever helps you keep that in mind. All right, now let's do a few quick problems here. Okay, so this first one, all right, let's look at our starting material. Let's look at our Wittig reagent. Okay, here's our carbonyl, right? This is a ketone. Here's our Wittig reagent. Okay, here's our Wittig reagent. Fantastic. All right, so what we need to keep in mind here is this is the carbon, all right, that will be replacing the oxygen. Okay, so this is, let me highlight it actually, it'll be better. This carbon in our Wittig reagent, all right, it's the carbon right after all the phosphorus groups. All right, this carbon will be replacing this oxygen in our final product, right? Because this is going to be a Wittig reaction, okay? So let's draw this out. Let's draw our first step. All right, we know this double bond is no longer going to be to an oxygen, but to a carbon. Okay, cool. What do we have attached to this carbon? We have a hydrogen and we have this ethyl group. Now, we don't have to worry here about stereochemistry because our molecule is symmetrical. So really, you can add the ethyl group here and the hydrogen here, or the other way around, it is equivalent. This is exactly the same as you drawing it this way. And that's only because our molecule is symmetrical, okay? But remember our rule, all right? If it's just a simple alkyl group with our Wittig reagent, all right, then our cis product is our main product. Okay, but here there's no cis or trans because it's symmetrical. If this looked like this, I'm going to give you an alternative to what this problem could look like. If this is the ketone we were reacting with our Wittig reagent, okay, our Wittig reagent, here's the carbon that's going to replace the oxygen, all right, we have a simple alkyl group. So that means we want the cis product as our major product. All right, we replace the oxygen with a carbon. All right, where do we add our ethyl group? Where do we add our ethyl group right here? To the side that will give us a cis product. All right, so you want all your biggest groups on the same side. All right, so that means we add our ethyl group to the left to match the fact that this is the bigger group. All right, so this would be our cis product. Okay, but that wasn't the problem. I was just giving you a modification to help you reinforce what we just talked about in terms of how you would proceed with drawing the major product if you had additional groups on your Wittig reagent. Okay, just to reiterate because it's so important. All right, if your Wittig reagent contains a group that's just a simple alkyl group, your major product is your cis product. If it contains pretty much any other group, your major product is your trans product. Okay, now one thing to keep in mind, all right, this is important, all right, there are variations of the Wittig reaction, all right, we learned it with this Wittig reagent that looks like this. It has these three phosphorus groups, right? Well, there is a kind of analog for that that's called your Horner Wadsworth Emmons reaction. All right, that has a that simplifies to actually HWE. All right, now the reagent for this looks similar, except that it doesn't have any of the phosphor groups or the phenyl groups. Okay, it looks something like this. All right, so this is an HWE reagent. All right, but this reaction is gonna proceed very similarly to a Wittig reaction. All right, what happens here actually is, ignoring this group, all right, this is going to be analogous to this group that we ignore. This part of the molecule is what we will be swapping off with the carbon. All right, so I'm going to go ahead and erase this, and we're going to try to work through this with this Wittig reagent analog. Okay, that's what we're going to call it. All right, what happens here is these electrons right here, all right, are gonna start to serve as the nucleophiles of this reaction, where our carbon here is going to be the electrophile. What happens simply is that we're going to replace this group. All right, it's going to swap out with this oxygen right here. So we keep the same structure here. We still have our hydrogen right there. All right, we still have our methyl group right here, and this double bond still persists. All right, this double bond still persists, and what you form here is the addition of this. All right, so this is swapping over here, so this carbon is this carbon that forms right here, and then we're going to go ahead and attach the rest of this reagent to it. All right, so this is the product for this reaction. Now, if this is confusing, this is fine. This was just an example I wanted to do to introduce Wittig reagent analogs. But for the most part, just focus on your normal Wittig reagents and try to master doing these problems. All right, now the last carbon nucleophile reaction that we want to talk about is the Bayer-Villiger oxidation. Now, when you take a ketone or aldehyde and you treat it with peroxy acid, what you can do is ketones can be converted into esters via the insertion of an oxygen atom. All right, so the proposed mechanism for this reaction is shown right here. All right, the peroxy acid is going to attack the carbonyl group of the ketone. All right, that's going to give us this intermediate that's going to undergo intramolecular proton transfer. All right, and then you have the final carbon-oxygen double bond is reformed by the migration of the R group. So this rearrangement, this final step of rearrangement, is going to produce the ester. So let's look at this. Here's your ketone. All right, your peroxy acid is going to function as a nucleophile. It's going to attack this carbonyl. All right, then you have a proton transfer from one location to another, intramolecular. All right, intramolecular proton transfer. Okay. Then last, you're going to have the carbonyl group is reformed with a simultaneous migration of an alkyl group. So this rearrangement is going to give us our final product. Now, the transfer migratory aptitude is as follows. A hydrogen site is the most preferred for oxygen insertion, all right, followed by tertiary sites, followed by secondary or phenyl sites, followed by primary, and then finally your least likely place for migratory sites is your methyl. All right, methyl is your least preferred site. So let's really just do a few problems to understand this, because that's really the best way to get this. All right, you have this starting ketone. Here's your peroxide. All right, you're treating this with a peroxide. All right, so now your question that you should ask is, well, all right, here is my molecule. All right, this is a non-scientific way of drawing this, really, okay? Here is, right here, all right, here's the site where my carbonyl is. Okay, I'm going to draw two empty sites to this molecule, all right? So I know in this picture they're all connected, but I'm just going to do something really quickly. I'm going to separate this half this left side of the carbonyl and this right side of this carbonyl. All right, we're going to leave a little bit of gaps on both sides. All right, this is where our thinking has to come into play. All right, which side of the carbonyl are we going to add our oxygen, right? Because we have a ketone reacting with a peroxide. All right, we already know this is a Bayer-Villiger oxidation, which means we're going to introduce an oxygen on some side of the carbonyl group we have in this molecule. The question now is, which side do we add it to? All right, that's the hard part to answer. Well, now we have to refer to our hierarchy, our migratory aptitude hierarchy. All right, which side is going to be more preferred? Well, on this side, all right, you have a primary carbon. This carbon has this one other group that it's attached to. All right, but on the other side, this carbon right here, this carbon is secondary. Well, which is preferred? Primary or secondary? Well, first it's hydrogen, then it's tertiary, then it's secondary or phenyl, which is what this position is right here, then primary. So obviously, this side takes priority over the other side. The left side is going to take priority over the right side. So that means when we draw our final product, all right, when we draw our final product, we're going to add the oxygen to the left side of the carbonyl. All right, so that means here goes our oxygen, then comes our carbonyl, all right, and then the rest of our molecule. So this is what our final product looks like. Okay, fantastic. Now, let's do B, and I'll leave C for you to do, all right? So one more, B. Okay, here is our molecule. All right, and I'm going to leave a gap again. All right, I'm going to leave a gap here because one of these sides is we're going to have to introduce a oxygen to. Why? Well, because we have an aldehyde and we have a peroxy acid. We already know this is going to be a Bayer-Villiger oxidation. Okay, now the trouble is finding out which site do we add the oxygen to. Well, we have a hydrogen on one side, and then we have this secondary carbon on the other side. Let's go back to our hierarchy. What is the most preferred group to add an oxygen to? Well, a hydrogen site is the most preferred for oxygen insertion. And guess what? We have a hydrogen right here. So what that means is we're going to add our oxygen right next to it. So our final product is going to look like this. We're going to add an oxygen to our hydrogen. All right, fantastic. All right, and that is what we get as a product. Again, I'll leave C to you to do. If you have any questions, please leave them in the comments. That's what I'm here for. I want to help. And if you want more problem sets for these practice problems, if you want more of these kinds of problems, just ask. I'll happily do it. All right, now we're pretty much coming to an end to this chapter. All right, we're just going to cover this last topic of the chapter, and that's really synthesis, and that's kind of the last topic of every chapter in organic chemistry. After you've learned new reactions and new preparations of certain groups, right, you kind of have to sit back and reflect on all the new synthesis pathways that you've learned. And for this chapter, you've learned a lot of synthesis problems, synthesis pathways for ketones and aldehydes with a variety of different nucleophiles. All right, we have really expanded our toolbox of reagents and pathways. And now when we approach synthesis problems, we have some new pathways to consider when approaching the problems. We have new techniques, we have new tools in our toolbox. The important thing to remember with synthesis is that there is more than one way to accomplish it usually. All right, so you can get as creative as you want. It's not usually just one right way. Sometimes you can be creative and you can do the synthesis through different sets of reagents and still get the end product that the problem is asking you for. All right. Now, it is important to kind of have a place that keeps tracks of all the pathways you've learned, from organic chemistry 1 included, because these problems will force you to recall some of that material. Now, I can always make a cheat sheet for you with all the reactions and pathways. I'm happy to do that if you want. All right, but it's also really important that you do a lot of practice problems. Commit to that. Even if it's just one problem a day, consistency is key, especially with synthesis. It really is the only best way to do this, to really get good at this, is practice, practice, practice. And with that, we segue into practice problems. Okay? Excuse me. All right, so we're going to look at these. We're going to look at this A problem. All right, we have this starting material. All right, this is our starting place, and we want to end up with this product, okay? So, how do we do this? What do we know from this chapter? Well, what we know from this chapter is we know how to form this carbon-carbon double bond right here. All right, we know what the prerequisite to get this carbon-carbon double bond. We covered it when we talked about Wittig reagents. If we had somehow a carbonyl at that site, all right, ooh, let me draw that way better. All right. If we had some sort of carbonyl group here, we know how to convert this into an alkene group, a carbon-carbon double bond. All right, but now this brings up a problem. How the hell are we going to get a carbonyl attached to this position so that we can finally convert it to a carbon-carbon double bond? Well, at the start of this chapter, we covered a way to prepare. All right, we covered a way to prepare ketones. All right, we know how to prepare ketones. If we start off with a secondary alcohol, all right, we can use some sort of reagents like sodium chromate, all right, sulfuric acid, and water, and we can convert the secondary alcohol to a ketone. All right, so that's one way we know how to do this, okay? So in our thinking process, we were like, hey, we know a way to get a carbon-carbon double bond. We just learned this. We can use a Wittig reagent, a simple Wittig reagent where the carbon just has two hydrogens on it, right? This carbon will replace this oxygen, and then we have the two hydrogens there. Perfect. All right, so if we possibly had a carbonyl there, we can get it to a double bond. But how are we going to get this carbonyl? Well, if we had an alcohol here, okay, if we had an alcohol here, we know how to convert the secondary alcohol to a carbonyl using sodium chromate, sulfuric acid, and water. But, all right, but how do we get an alcohol on there? Okay, well, we can reflect. We can reflect on some of our elimination and substitution reactions way back in the days of Organic Chemistry 1. We know how to add alcohol groups. All right, our addition reactions from Chapter 8. If we happen to have a double bond here, for example, all right, we can do some hydroboration oxidation. All right, THF and H2O2 and sodium hydroxide. And guess what? This is going to add, via anti-mark, a alcohol group to that double bond. All right, so if maybe we had a double bond right here, we would know how to get an alcohol group attached there, and then we could take that alcohol group, we can convert it to a carbonyl, and then we know how to take that carbonyl and convert it to a double bond. All right, but we're just causing one problem after another, because now, how the hell are we going to get a double bond there? Right? How are we going to get a double bond there? All right, how do we even get that? How do we even get an elimination reaction to lead us there? Well, all right, this requires some more thinking. What if we can somehow get some halogen here? All right, some sort of halogen like bromine, for example. All right, and then use a strong base, all right, a strong base to do an elimination reaction and have a double bond form there. All right, we covered this in Chapter 7, right? E2 reaction, elimination reactions. Okay, but then this brings up the issue again. How are we going to get a bromine? All right, how are we going to get a bromine to our starting material? Well, we also covered this, guys. We can add a bromine there. Easy peasy. All right, NBS and light. All right, this is going to add a bromine group there. All right, so we kind of just worked through this backwards. All right, this is called retrosynthesis. All right, taking the end product and working backwards from there. All right, we know that the difference between our starting material, all right, the difference between our starting material and our end material, all right, is this double bond right here. All right, and now we can work backwards. Well, we can get that double carbon bond if we started off with a carbonyl group there and reacted with a Wittig reagent, we would get this product. All right, but then you would have to go back one step. Well, how did we get that carbonyl in that position? Well, if we had a secondary alcohol, we know how to convert a secondary alcohol into a ketone, for example, and have this carbonyl group there. All right, but then you ask, how would we even get that alcohol group in that position to begin with? To then convert it into a ketone, well, we could always have an addition reaction. We could have a double bond right here and then add a water to one side and a hydrogen to another to the double bond. And boom, now we have an alcohol group here. Well, then one more question. Well, another question is like, well, where did we get that double bond from? How do we form that double bond there? Well, if we had some halogen group nearby, we can do an elimination reaction and form that double bond. And we know the reagent to use that because we covered that in chapter 7. And now your final question to ask is, well, how did we get a halogen on there? Oh, we can use NBS and light to add a bromine there. All right, so we just worked backwards from the reaction. Now I'm going to erase all this, and we're going to work from it backwards in a prettier picture way now that we've talked about this, okay? So I'm going to erase this really quick, and we're going to draw it again, no worries, but slightly better. All right, slightly better. So let's erase all of this. And let's draw the synthesis pathway for this. Again, there's more than one way to do this. So if you have some ideas and you want to share, feel free to comment in this comment section below, and we can talk about it. All right. So here we go. Here's our starting material. All right. Here's our end product. All right. Here's our end product. Now we talked about this to get this carbonyl group right here. All right. If we had a carbonyl group here, we can convert this carbonyl group right here into a carbon-carbon double bond using our Wittig reagent. All right, so if we had PH3P, all right, that's double bonded to a carbon with hydrogens right here, right? That's our Wittig reagent. Let me circle that in a different color. All right. We can use this Wittig reagent to convert this carbonyl into that double bond. All right, but how did we get this carbonyl again? All right, well, we started off with a primary. If we had a secondary alcohol here, we can oxidize this using sodium chromate and sulfuric acid and water. All right, these reagents will take this alcohol group, convert it to this carbonyl group right here. All right, but how did we get that alcohol to begin with? All right, this is what we talked about. All right, if we had a double bond right here, that would be really nice because now we can do an addition reaction to the double bond. All right, we can use BH3 and THF. All right, and then H2O2 and sodium hydroxide. That way we can to this double bond, using these reagents, we can add an alcohol group to one side and a hydrogen to the next. All right, but then how did we get that double bond to begin with? Well, that's a great question. What if we had a halogen somewhere here, for example, that we can then convert into a double bond through an elimination reaction? Oh, that would be easy. We can use like sodium ethoxide. You can even use tert butoxide if you liked, whichever bulky base you would like to use. All right, would get the job done. It would do an elimination reaction, all right, where we would form a double bond right here. All right, but then our last question is, well, with our starting material, how can we add a bromine there? Well, we can use NBS and light. Or you can actually even use, what would be better here is Br2 and light. and that would add a bromine group here. Fantastic. Then you can eliminate this bromine group through an E2 reaction using a bulky base. Now you have a double bond here. Beautiful. We can do an addition reaction, hydroboration. All right, anti-mark. Now we have our alcohol group in the least substituted place. This is a secondary alcohol. We can oxidize secondary alcohols into carbonyl groups, and then using our Wittig reagents, we can convert that carbonyl into our carbon-carbon double bond. All right, so sometimes working through a synthesis problem might include a lot of steps like this one. And you can work forward or you can work backward, whichever way you prefer, or you can do. And sometimes it takes trial and error, and there is usually more than one way to do it. So make sure you do a lot of practice problems. I'm going to leave B for you to do. All right. Post your answers below and I'll let you know if your synthesis pathway is correct and logical, and we can have a conversation. All right. But make sure you do lots of practice problems. With that, that is the end of chapter 19. We have finished chapter 19. If you have any questions, let me know. Other than that, good luck, happy studying, and have a beautiful day.